Welcome to the deep dive.
Yeah.
We're all about cutting through all that noise,
Yeah.
and getting to the heart of complex topics.
Hmm.
Today, we're going to dive into the world of the Ensemble Kalman Filter.
Yeah.
And this technique, well, it's used to predict the state of systems, complex systems, even when we are absolutely drowning in data.
Yeah.
So think weather forecasting or climate modeling, you name it.
Yeah. It's a really powerful tool that has applications across a wide range of fields.
And our guide for this deep dive,
Okay.
it's this article. It's called Understanding the Ensemble Kalman Filter.
Uh-huh.
And it's from the American Statistician.
Okay.
It lays out the essentials of this technique, and we are here to make sure that you walk away with, well, a solid understanding of what it's all about.
Okay.
So let's get started with the basics. What exactly is a Kalman filter?
Well, at its core, a Kalman filter is a way to estimate the state of a system that changes over time. So imagine you're tracking a moving object, but you only get these glimpses of it every so often. The Kalman filter, it combines those observations with what we know about how the object usually moves to estimate its most likely position.
So it's kind of like a detective, like piecing together clues to try to track a suspect's movements.
Exactly. But instead of relying on hunches, the Kalman filter uses this mathematical framework, and it combines those observations with a model of how the system evolves. And the really cool part is that it doesn't just give us like a single best guess. It provides a whole probability distribution, and it shows us the range of possible states and how likely each one is.
So instead of just saying the object is probably here, it's saying, well, there's a 90% chance that it's within this area, and here's the most probable trajectory, right?
Exactly.
That seems incredibly useful, especially when you're dealing with complex systems where there's a lot of uncertainty.
Absolutely. And that's where the Kalman filter really shines. It's been used in all sorts of things,
Right.
like tracking spacecraft or predicting the spread of diseases.
But I imagine there are some limitations. What happens when you're dealing with, incredibly complex systems with tons and tons of variables, like a whole weather system, or a global pandemic?
Yeah, that's where the traditional Kalman filter starts to run into some problems.
Okay.
It starts to hit a computational wall, trying to represent the entire probability distribution for a system with, millions of variables would require an immense amount of computational power.
So it's like trying to solve, I don't know, a Sudoku puzzle the size of a city.
Okay.
It would just take forever.
Right. Yeah, that's a great analogy. And that's where the Ensemble Kalman Filter, or EnKF, steps in. And it provides a clever workaround for these, high-dimensional problems.
Great. So how does it do that?
Well, instead of trying to work with the entire probability distribution, which would just be computationally impossible in these cases, the EnKF uses a smaller set of possible states called an ensemble.
So instead of trying to track every single raindrop in a storm, we're saying, let's just focus on like a representative group of raindrops and see how they behave.
Precisely. And each member of the ensemble represents a possible state of the system. It's like having a bunch of arrows all pointing in different directions. Each one represents a potential path the system could take. As new data comes in, those arrows are adjusted to reflect the updated probabilities.
So it's a way to simplify the problem without sacrificing too much accuracy, right?
Exactly. And that simplification makes it possible to apply the Kalman filter to much larger and more complex systems.
That's pretty amazing. So we've got these arrows representing the possible states of the system. How exactly are those arrows updated when new data comes in?
So there are two main approaches that are used: stochastic updates and deterministic updates.
Okay.
Stochastic updates introduce a bit of randomness into the system, and this helps to kind of explore a wider range of possibilities and avoid getting stuck in a narrow solution.
So it's like shaking up a snow globe to see how the flakes settle differently every time.
That's a good way to think about it. On the other hand, deterministic updates aim to minimize uncertainty.
Okay.
They shift the ensemble in a more controlled way.
So it's like carefully adjusting a telescope to get a clearer image.
Exactly. And the choice between stochastic and deterministic updates depends on the specific application and the characteristics of the system you're trying to model.
Now, I'm curious about how the EnKF is actually used in these real-world situations. Are there any specific techniques or tricks that researchers use to make it even more effective?
Yeah. There are several key techniques.
Okay.
One is variance inflation.
What's that all about?
Variance inflation is a way to avoid underestimating uncertainty.
Okay.
Remember those arrows, right?
Representing possible states.
Right. Variance inflation essentially spreads those arrows out a bit further.
Okay.
It's acknowledging that our model might not be perfect and things could change more dramatically than we initially thought.
So it's a way to build in a safety margin to account for the unexpected.
Exactly. It's a way to acknowledge that we don't have all the answers and to make our model more robust to surprises.
Makes sense. What are some of the other techniques used to improve the ENKF?
Another important technique is localization.
Okay.
It's based on the idea that observations made in one location are more likely to be relevant to nearby locations than to those further away.
So if we're trying to, I don't know, like predict the weather in New York City, we shouldn't give too much weight to temperature readings from Los Angeles.
Exactly. Localization helps to avoid those spurious correlations between things that are far apart,
Okay.
and it allows the ENKF to focus on the most relevant data.
So it's all about, filtering out the noise and zeroing in on the signal, right?
Nice. And another technique worth mentioning is serial updating.
Okay.
Instead of trying to process all the observations at once, serial updating breaks the problem down into smaller, more manageable steps,
Okay.
handling each observation one at a time.
So it's like eating a giant pizza one slice at a time instead of trying to swallow the whole thing at once.
That's a good way to visualize it.
Yeah.
And this approach can significantly improve computational efficiency, especially when you are dealing with large data sets.
It seems like the ENKF is a really versatile tool. It's fascinating how these techniques take these sophisticated mathematical concepts and translate them into practical solutions for real-world problems.
It is. And we haven't even touched on the fact that the ENKF can do more than just filter data. It can also be used for smoothing, which is like looking back in time, refining our understanding of past events, almost like you're reconstructing a historical timeline. But we can dive into that a bit later.
Okay, that sounds intriguing. But before we move on, I'm curious about something you mentioned earlier. You said that the ENKF is designed for linear Gaussian models. But it often works surprisingly well, even when those assumptions are broken. How is that possible?
That's a great question. And it gets to the heart of why the ENKF is such a powerful tool. The key lies in a concept called linear Bayesian estimation.
I have to admit that's a term I'm not entirely familiar with. Could you shed some light on it?
Of course. Essentially, linear Bayesian estimation allows us to make reasonable estimates even when we don't know the exact shape of the probability distribution. It's like drawing a rough sketch of a landscape based on limited information. But that sketch can still be surprisingly useful for navigation.
So it's a way to kind of deal with uncertainty and make informed decisions, even when we don't have all the pieces of the puzzle.
Exactly. And that's one of the things that makes the ENKF so robust and adaptable. It can handle situations where the real world doesn't perfectly match our mathematical models.
That's really impressive. So we've covered a lot of ground here already. We've talked about what the Kalman filter is, how the Ensemble Kalman filter addresses the challenges of high-dimensional data, and some of the key techniques used to make it even more effective. But I'm eager to learn more about those additional capabilities that you mentioned, like smoothing and parameter estimation.
Absolutely. Let's dig into those next. So before we move on to those other capabilities of the ENKF, it's worth spending a little more time on this idea of linear Bayesian estimation
Okay.
and how it allows the ENKF to kind of handle these nonlinear systems.
Okay. Yeah, you mentioned that the ENKF is designed for linear systems, but often works surprisingly well even when the system is nonlinear.
Right.
It seems almost counterintuitive
It does.
that a method designed for straight lines could handle curves so well.
Right. And the key to understanding this is remembering that the ENKF is fundamentally about updating our beliefs based on new information.
Okay, so we start with an ensemble representing our initial understanding of the system. And then we use observations to kind of nudge those beliefs in the right direction.
Exactly. Now, in a linear system, those nudges, those can be calculated very precisely using matrix equations.
Okay, but in a nonlinear system, the relationship between the state variables and the observations,
Right.
it can be much more complex.
It can be much more complex. Yeah. It's like trying to navigate a winding mountain road instead of a straight highway.
Okay.
But here's the key. Even in those twisty nonlinear scenarios, we can still use the ENKF to make those nudges
Okay.
and update our beliefs.
So how does that work? I'm imagining like trying to fit a square peg into a round hole.
Well, the ENKF doesn't ignore the nonlinearity.
Right.
It actually embraces it by applying those nonlinear operators to each ensemble member individually.
So it's recognizing that each possible state of the system might follow a different path
Yes.
through that nonlinear landscape.
Precisely. And by doing this, we're essentially capturing the nonlinear dynamics of the system within our ensemble.
That's clever.
Yeah.
So we're essentially allowing each ensemble member to kind of navigate that winding road independently.
Uh-huh.
And then we're using those observations to guide them towards the most likely destination.
You got it. And it turns out that even though those updates might not be perfectly accurate because of the nonlinearity, they're often good enough to provide valuable insights.
It's fascinating how the ENKF can handle those complexities without getting bogged down in the mathematical weeds.
It really is a testament to the ingenuity of the approach.
Yeah.
And speaking of handling complexities, the ENKF is also surprisingly robust to non-Gaussian distributions.
Oh, that's interesting. So we talked earlier about how the ENKF assumes a Gaussian distribution.
Right.
You know, that familiar bell-shaped curve.
Yes.
But what happens when the real-world data doesn't fit that neat Gaussian mold?
Yeah, that's where linear Bayesian estimation comes in again.
Okay.
It turns out that even when the underlying distribution is non-Gaussian, maybe it's skewed or has multiple peaks, we can still use linear Bayesian estimation to make decent estimates based on just the mean and variance of the data.
So it's like saying, even if our map isn't perfectly accurate because the landscape is more complex than we thought, we can still use like the average elevation and the general roughness
Right.
to get a sense of where we are.
Exactly. And it's this flexibility that makes the ENKF such a powerful tool when faced with real-world data, which is often messy and unpredictable.
Yeah, it's like a seasoned traveler who knows how to adapt to unexpected situations and still reach their destination.
Uh-huh.
But even with all its strengths, I imagine the ENKF has its limits.
Oh, of course.
Are there situations where it starts to break down?
Yeah, that's an important point. The ENKF isn't a magic bullet.
Right.
It does have limitations,
Sure.
especially when those non-Gaussian deviations become too extreme or the nonlinearity is too severe.
So what do researchers do in those cases? Do they just give up and go home?
Not at all. They've developed various extensions and modifications to the ENKF to address those challenges.
Okay, so could you give us a taste of what those might be?
Yeah, one approach is to use a technique called state augmentation.
Okay.
And here we essentially expand the state vector to include additional variables that capture the nonlinearity or the non-Gaussianity.
So it's like adding more detail to our map to account for those hidden valleys and treacherous peaks that weren't on the original version.
Precisely.
Hmm.
And by doing this, we can often bring the problem back into a form that the ENKF can handle more effectively.
That's clever. So it's not just about using the ENKF as is, it's also about being creative
Right.
and adapting it to the specific problem at hand.
Exactly.
What other approaches are there?
Another approach is to combine the ENKF with other filtering methods,
Okay.
like particle filters, which are better suited for highly nonlinear or non-Gaussian scenarios.
Okay.
It's like having a team of explorers with different skills and expertise all working together to map out the unknown.
So it's all about choosing the right tool for the job,
Yes.
and sometimes even combining tools
Right.
to create an even more powerful solution.
Exactly.
I love how the ENKF has inspired so much innovation in the field of data assimilation.
It really has. And one of the things I find most impressive is how it's fostering communication and collaboration across different disciplines.
Yeah, we've talked about the ENKX journey from geophysics to other fields, but it's remarkable how it's become this common language,
Right.
connecting researchers from all walks of life.
It really is the key to unlocking its full potential,
Yeah.
sharing knowledge and insights across disciplinary boundaries.
Yeah, I couldn't agree more. The more we learn from each other, the more we can push the boundaries of what's possible.
Uh-huh.
But it's also important to remember that the ENKF isn't a static tool.
Right.
It's constantly evolving.
It's like a living organism. It adapts and grows over time.
Yeah.
As we encounter new challenges and explore new frontiers in data assimilation,
Yeah.
we can expect the ENKF to continue to play a vital role in helping us make sense of the world around us.
Yeah, that's exciting to think about. But before we get carried away by the future, I think it's important to take a moment to appreciate the elegant simplicity of the ENKF.
Absolutely. At its core, the ENKF is about combining prior knowledge with new observations
Yeah.
to update our understanding of a system.
It's such a fundamental principle that we use in countless aspects of our lives.
Right?
Whether we're consciously aware of it or not,
Yeah.
we adjust our driving route based on traffic reports.
Uh-huh.
We modify a recipe based on how it tastes.
We even form our opinions and beliefs based on new information and experiences.
Exactly. It's this intuitive process
Mm-hmm.
that the ENKF formalizes, but instead of relying on gut feeling or guesswork. It uses this systematic mathematical framework.
And that framework allows us to handle much more complex scenarios and make more reliable predictions than we ever could on intuition alone.
It's like having a more sophisticated way to process information
Right.
and make decisions in a world that's increasingly complex and data-driven.
Precisely. And it's that blend of intuitive appeal and mathematical rigor that makes the ENKF such a powerful and versatile tool.
So we've covered a lot of ground here. We've explored the ENKF's ability to handle nonlinearity and non-Gaussianity.
Uh-huh.
We've touched on some of the techniques used to enhance its performance.
Right.
And we've even talked about its role in fostering interdisciplinary collaboration.
Yeah.
But there's still one capability you mentioned
Uh-huh.
that we haven't delved into yet,
Right.
and that's parameter estimation.
That's a crucial aspect of the ENKF.
Yeah.
And one that opens up a whole new world of possibilities.
Okay, let's dive into that.
Yeah.
So we've talked about how the ENKF can be used for filtering and smoothing,
Right.
but now let's dive into this idea of parameter estimation.
Okay.
What exactly does that mean in the context of the ENKF?
Well, parameter estimation is all about figuring out the best values for those unknown parameters in our model.
Okay.
Based on the data that we observe, it's kind of like trying to fine-tune a musical instrument, to get the perfect sound.
So it's not just about tracking the state of the system. It's also about understanding those underlying mechanisms that drive its behavior.
Exactly. And the paper highlights two main approaches to parameter estimation within this ENKF framework.
Can you walk us through those approaches?
Sure. The first approach is called state augmentation.
Okay.
And here, we essentially treat the unknown parameters as if they were part of the state vector itself.
So instead of just tracking those variables that describe the system's current state, we're also trying to estimate those, those hidden knobs and dials that control how the system evolves over time.
Precisely. And by including those parameters in the augmented state vector, we can use the ENKF to estimate their values along with the state variables.
That's an interesting way to think about it. It's like we're expanding the ENKS scope.
Yeah.
To include not just the what of the system, but also the why.
Exactly. And this approach works well in many cases, especially when the parameters are relatively well behaved.
But what about situations where the parameters are more complex? Maybe they vary over time or have these nonlinear relationships with the state variables.
Yeah, that's where the second approach comes in, which is based on constructing approximate likelihood functions.
Wow.
Using the output from the ENKF.
So instead of directly estimating the parameters, we're using the ENKF's predictions to infer what those parameters must be.
Exactly. We're essentially using the ENKF as a detective, to gather evidence, and then we use that evidence to build a case for the most likely values of the parameters.
That makes sense. So the ENKF is doing the heavy lifting of predicting the system's behavior, and then we use those predictions to kind of work backward and figure out what those underlying parameters must be.
You got it. And as with any good detective work, the more evidence we have, the more confident we can be in our conclusions.
The paper mentions that these likelihood-based methods tend to work best when the number of parameters is relatively small. What happens when we're dealing with systems that have, a huge number of parameters to estimate?
Yeah, that's a real challenge. And it's an area of active research in the ENKF community.
Oh,
One promising direction is to explore the use of techniques from, machine learning and statistical modeling to handle these high-dimensional parameter estimation problems.
So it's like bringing in a team of, expert statisticians and data scientists to assist with our detective work.
Exactly. And by combining the strengths of the ENKF with these advanced statistical methods, we could potentially unlock new levels of accuracy and insight.
That's exciting. It seems like the ENKF is not just a powerful tool on its own, but also a catalyst for innovation in other fields.
Absolutely. And as we wrap up this deep dive, I think it's worth highlighting one more aspect of the ENKF's future that I find particularly inspiring.
I'm all ears. What is it?
It's the growing recognition of the ENKF's potential to address some of the most pressing challenges facing humanity today. Things like climate change, natural disasters, and public health crises.
It's incredible to think that this, mathematical technique developed for filtering noisy data could have such a profound impact on the real world.
It is. And by providing us with better forecasts and a deeper understanding of these complex systems, the ENKF can empower us to make more informed decisions and take more effective action.
So it's not just about advancing our scientific understanding, but also about, translating that understanding into tangible solutions for a better future.
Precisely. And just as importantly, the ENKF can help us to quantify those uncertainties associated with our predictions. And that's really crucial for making sound risk assessments, and developing robust mitigation strategies.
Yeah, that's a really important point. It's not just about making predictions, it's also about understanding those limits of our knowledge and acknowledging the possibility of surprises.
Exactly. And by embracing this humility and acknowledging the inherent uncertainties in complex systems, we can make more responsible and sustainable decisions.
So it's about combining, scientific rigor with a healthy dose of caution and awareness of what we don't know.
Precisely. And it's this blend of technical expertise and ethical awareness that I believe will ultimately determine the ENKF's legacy.
Yeah, it's a legacy that has the potential to shape the future of our planet and the well-being of generations to come.
It really does. And it's a legacy that we all have a role in shaping through our continued support for scientific research, education, and outreach.
Well said. This has been an incredible journey into the world of the Ensemble Kalman Filter. We've explored its inner workings, uncovered its hidden strengths, and glimpsed its potential to shape the future. I feel like I've gained a whole new appreciation for the power and beauty of this remarkable technique.
Well, it's been a pleasure diving into this topic with you, and I hope our listeners have come away with a newfound curiosity about the ENKF and its role in understanding and navigating our complex world.
I'm sure they have. And to our listeners, we encourage you to continue exploring this fascinating field. There's so much more to discover. So until next time, keep those minds curious and those questions flowing.
And as always, thanks for joining us on the deep dive.